A linear first order differential equation is an equation of the form a sub 1 of x dy dx plus a naught of x times y is equal to g of x. Now, if we divide everything by the leading coefficient a1 of x, then we can write this in the form dy dx plus p of xy is equal to f of x, where p of x is a naught of x divided by a1 of x, and f of x is g of x divided by a1 of x. This is said to be the standard form. Furthermore, if f of x is 0, then the equation is said to be homogeneous. Let's now look at some differential equations. We will determine if it is linear or not. So start with x prime equals negative 3x plus sine of t. We'll rewrite this. We can write as dx dt plus 3x is equal to sine of t. Well, this is clearly linear. We have p of t is equal to 3, and we have f of t is equal to sine of t. Next, let's look at the equation. X prime equals x times sine of t plus t cubed. Again, we can rewrite this. Dx dt minus x sine of t is equal to t cubed. Now again, this is linear. We have p of t, in this case, is sine of t, and f of t is t cubed. So now for x prime plus e to the x, t is equal to 0. Right away we can tell this is not linear, because we have e to the x. Finally, x prime is equal to 2t. Again, this is clearly not linear, because the coefficient of dx dt is x. Let's now consider method of solution. We will first consider the homogeneous case. That is, we have dy dx plus p of x times y is equal to 0. Now, what we can do is we can rewrite this. Dy dx is equal to negative p of x times y. Well, notice that this is separable. So we can write dy over y is equal to negative p of x dx, which means that the antiderivative of dy over y is equal to the antiderivative of negative p of x dx. So we have log absolute value of y is equal to negative antiderivative p of x dx. So the general solution has form y of x is equal to e to the negative integral p of x dx. Now, we will usually choose the simplest function. So the simplest antiderivative, that is, we will choose the simplest little p of x such that little p prime is capital P of x, which will allow us to write this now in the form y of x equals alpha e to the negative little p of x, where alpha is just some constant. So either of these two forms. So let's go ahead and solve a linear equation. So dy dx plus y cosine of x is equal to 0. Well, rewrite this. Dy dx equals negative y cosine of x, which of course means that dy over y equals negative cosine x dx. So the integral of dy over y is equal to the integral of negative cosine x dx. So we get log absolute value of y is equal to negative sine of x plus an arbitrary constant. So absolute value of y is equal to e to the negative sine x plus this constant, which is just a constant times e to the negative sine of x. So we get as our solution y of x equals a constant, e to the negative sine x. Now notice what I did here was I actually went through each step instead of just referring to what we derived earlier. This is what is recommended. It is not recommended that you just memorize the general form of the solution. Instead, you should put it to practice and show all of your work each and every time. We now consider the non-homogeneous case. So we have dy dx plus p of x times y is equal to some function f of x. Now, this all hinges on the fact that the left-hand side of this equation can be recast into the form of the exact derivative of a product by multiplying both sides by a special function. We call this function mu of x. So, this means that what we want is we want to multiply both sides by mu. So we want a function mu of x satisfying d dx mu of x times y, which remember equals, by the product rule, mu of x times dy dx plus d mu of x dx times y, and we want this to equal mu of x times dy dx plus mu of x times p of x times y. So this is true provided that d mu dx is mu of x times p of x. We can solve for mu now by using separation of variables. So we get d mu over mu is equal to p dx. So we now have the log absolute value of mu is equal to the integral of p dx plus, call it some constant. So what we find is that mu is equal to some constant e to the integral p dx. Now we can simplify this by setting c to be just 1. Therefore, our mu is simply e to the integral p dx. We call this an integrating factor. Well, now we come back up and we replace mu with what we just found. So notice what we now have. We get e to the integral p dx dy dx plus p of x times e to the integral of p dx y has to equal e to the integral of p dx times f of x. This will give us that d dx of e to the integral px dx y is equal to e to the integral of p of x dx times f of x. We can now integrate both sides, and we get e to the integral of px dx times y is equal to the integral of e to the integral p of x dx times f of x dx plus some constant c. We now solve for y, and we get a general solution of the form y of x equals e to the negative integral p of x dx times the integral of e to the integral p of x dx f of x dx plus c times e to the negative integral p of x dx. So let's try solving one. So let's look at the equation. Y prime is equal to y plus x e to the x. Well, first let's put this in standard form. So let's call rho of x to be the integral of -1 dx, which of course is simply negative x. This means that our integrating factor, mu of x, will be e to the negative x. Now we multiply both sides of our standard form by this mu of x, and we get e to the negative x dy dx minus e to the negative x times y is equal to x e to the x times e to the negative x, which is just simply x. Now, this here is a product rule. So we have d dx of e to the negative x y is equal to x. So if we integrate both sides, we're going to get e to the negative xy is equal to the integral of x dx, which is, of course, x squared over 2 plus an arbitrary constant. Therefore, y of x is e to the x squared all over 2 plus c e to the x. Let's look at one more. So let's now look at an initial value problem, x, y prime plus y is equal to cosine of x. Under the condition that y of 1 is equal to 2. So we again need to put this into standard form first. So we're going to have dy dx plus y over x is equal to cosine of x over x. As we did before, let rho of x be the integral now of dx over x. Right, I'm getting this dx over x from this term. It's the integral of p of x dx. Well, this is log absolute value of x. So this means that mu of x is e to the log of absolute value of x, which is just simply the absolute value of x. So we multiply everything by absolute value of x. Now, without loss of generality, I'm going to assume that x is positive. So we can rewrite this as x dy dx plus y is equal to cosine of x. Once again, we have a product rule. So we get d dx of x times y is equal to cosine of x. And so x times y has to be the antiderivative of cosine of x, which is sine of x. And so y of x must be sine of x over x plus c over x. Now, since we're dividing by x, we have to have that x cannot be 0. We can now use the initial condition. That y of 1 is 2. And we get that 2 must equal sine of 1 over 1 plus c over 1. Now, sine of 1 is simply sine of 1. So c must be 2 minus the sine of 1. Now just leave c in this form. Don't approximate sine of 1. So our particular solution, sine of x over x plus 2 minus sine of 1 all over x. And again, we have to have that x cannot be 0.